And we can now move to the next paper, the last paper of this session. That is, not all videos become outdated. Show video recommendation by learning to deconfound release interval bias. The authors are Lulu, Guoxiu, Aixin, and the presenter is Lulu.
Good afternoon, everyone. My name is Lulu Dong, a graduate student from East China Normal University. Today, I'm honored to present our work as the first author. The second and third authors are my advisor, Guoxiu and Professor Aixin from Nanyang Technological University. In our paper, we found that short video recommender systems often show a bias towards newer videos. Our analysis using a causal graph for short video recommendations suggests that the time between a video's release and when users interact with it creates this bias. In other words, the system favors new videos, and we call this the release interval bias. This bias is made worse by the matching models that learn from past user interactions. To solve this, we developed a model-agnostic method called learning to deconfound the release interval bias, or LDRI for short. So why does this matter? We analyzed a real-world dataset called Querand1K, which is collected from the logs of the Guoxiu app. The release interval refers to how long it's been since the video was released. Figure A shows how exposure drops as videos get older. This clearly shows that newer videos make up 90% of total exposure. Figure B illustrates that as videos age, user interactions like watch time and favorite rates also drop. Since platforms aim to maximize positive feedback, models trained on these interactions may create a shortcut linking new videos with better feedback, further exacerbating this bias. However, not all videos become outdated over time. For example, Figure C shows that for certain topics, positive user feedback actually increases over time, meaning these videos are less sensitive to recency. Even older videos on these topics can still provide a good user experience. On the other hand, Figure D shows a typical drop in interest for other topics over time, meaning these videos are more sensitive to recency. Despite this, the system treats both topics the same, giving new videos an advantage. That's why it's important to address the release interval bias and create a more tailored recommendation based on how sensitive each video is to recency. To analyze and fix this, we use the causal inference. The figures in the paper show different processes for recommendation. Figure A illustrates the traditional recommendation method, where the matching score between users and videos determines the recommendation. However, this does not take into account how quickly videos become outdated. Figure B shows an ideal recommendation process that does. In this case, the causal effects of videos on user interest come from two factors: capturing users' attention and staying relevant over time. Unfortunately, in reality, recommendations often focus on newer videos, whether or not older ones are still relevant. Figure C highlights that the release interval creates a non-causal shortcut between newer videos and positive feedback, making the recommendation biased. Our proposed method, LDRI, uses a technique called backdoor adjustment to block these shortcuts and remove the bias. Simply put, the causal effect of a video on user interest is measured by changing the video status from a reference point to a target point, essentially intervening on the video. This removes the shortcut as shown in Figure D and eliminates the non-causal relationship. The remaining part of this formula is often simplified recognition tasks because we are mainly ranking videos. We can derive the model through the law of joints and marginal distributions. In the end, LDRI learns two things: the matching score between videos and users, and the recency sensitivity of each video. During inference, we use a filtering function to combine these two factors to make the final recommendation. Figure E demonstrates how LDRI works. In training, it uses a joint learning approach with a shared binary label to learn both the matching score and recency sensitivity, as shown in the left and middle parts. The left side shows how the matching score is learned using a backbone model, while the middle part represents our unique design that learns the recency sensitivity of each video. LDRI generates video embeddings from the video's features and projects them onto multiple dimensions. For each interaction, it calculates BCE loss using the binary label and the corresponding dimension, which equals the release interval. When certain dimensions of the sensitivity score have higher values, it means that the video still receives positive feedback at those release intervals, suggesting it's less likely to be outdated. The right part illustrates that during the inference stage, we fill the two scores by weighting, then use backdoor adjustment to make the final recommendation. Next, let me introduce the experiments we conducted. We used two datasets, 3 baselines from recent research, and 3 backbone models. The table on the right shows how our LDR model compares based on top K metrics and inference time. Overall, LDRI outperforms all 3 backbone models and sort time methods in nearly every metric, while maintaining a low computational cost. We also compared backbones without and with LDRI, as shown in Figure 4. Our results break down performance based on release intervals, and applying LDRI significantly improves NDCG scores across almost all intervals. Additionally, we evaluated the performance of the backbones, the sort time methods, and our LDRI in addressing the causal problem. Figure 5 shows that LDRI still outperforms the sort time models in this scenario. Finally, we conducted a case study on prediction scores to demonstrate how LDRI reduces bias. Figure 6 shows the difference in prediction scores between DeepFM and DeepFM with LDRI on recency sensitive videos. For these types of videos, it's best to recommend the newest content and reduce the exposure of older videos. We see a clear drop in prediction scores for older videos when LDRI is applied, helping to reduce their availability. For recency insensitive videos, since they remain relevant for longer, we expect the prediction scores to be more even across release intervals. As shown in Figure 7, when DeepFM is enhanced by LDRI, the scores for older videos increase. These results strongly demonstrate the deconfounding capability of LDRI. This concludes my presentation. We sincerely appreciate the constructive feedback from the anonymous reviewers. I'd like to express my gratitude to my advisor, Dr. He, and Professor Sun for their invaluable guidance. Thank you for your attention.
Okay, thank you, Lulu. Do we have questions from the physical audience? Again, don't be shy. Yeah, I can see a hand there and another there. So, please.
Okay, thank you for your presentation. I have some questions that it seems like you compare several baselines, and I would like to know how do you surpass them?
Okay. In response to your question, we do compare several baselines, like we compare TCCM, which incorporates the release interval as a feature into the model, but it may lead to an amplification of bias. We also compared a method called TAFR, which uses a survival analysis to model the temporal information of each video, but it relies on large amounts of interaction logs of each video to model accurately, and it often needs to manually determine a threshold to determine which video is dead. Also, we compared a method called DCR-MOE. Its performance is quite promising, but its time cost is rather high. Compared to them, our method does not require any feature engineering, and we maintain a relative low time cost.
Okay, thank you. And we have another question.
Yeah, thank you. Could you talk about how the ability to recommend those time-insensitive videos for longer can perhaps affect how users create video on your platform, since they are more likely to be recommended for longer? Do you think it would lead to people building videos that are not so time-sensitive?
In the process of learning recency sensitive representations, we incorporate the video feature, computed release interval, and the label Y from each interaction record. Leveraging video feature, we construct a representation T of length A. Subsequently, we use release interval as an index to extract the value as a corresponding position in T for training. This process forces a certain dimension of T to learn only the non-obsolete probability corresponding to the release interval. Yes.
Okay, thank you. Do we have other questions? Let me check on Slido. Okay, we received another. Okay, we have a question by Olivier. Thank you for the nice talk. Do you consider the selection bias? Maybe for the topic number 2, all the videos have a higher favorite rate because the production system accurately surfaces good content. And it's not a general statement we can make about topic number 2.
Well, I think this question is detailed, and I'd like to discuss it offline.
Okay, thank you. Let's thank Lulu again.
Thank you.